You are welcome to FANOG Research Group YouTube channel. Please click on the subscribe button to subscribe to our YouTube channel. You will get notified whenever new video is uploaded. Thank you.
Analysis. So uh, we are going to continue with that. That's the second course for us to look at. And if you recall, we said that one of the set that will play an important role for us in this course will be your X will be a linear space, or what you call a vector space, a vector space. Okay, I'm sure you recall what a linear space is. A vector space is a set together with two binary operation. Uh, the first binary operation is um, addition. So with respect to the first binary operation, you have this structure becomes an abelian group. We say what that is, and then with respect to the dot, that's the multiplication. You have the following. You have that you can always, number one, you always can have, there exists a 1 in that structure in X such that uh, 1 dot X is equal to X dot 1. We not change the value of X for all vector X in X. Number two is that you have the LDL, left distributive. In other words, if you have alpha into X plus Y, you have that alpha X, if alpha X plus alpha Y will coincide with this. You also have the right distributive loss, meaning that if you move your scalar to the right, you have the following. You have X dot alpha plus Y dot alpha. Okay. And not only that, you have that if you have alpha into X dot Y, it doesn't change the value of, we have alpha XY. So all those structures makes X what we call a vector space. So this is the structure we are going to be working with. So that to define, for instance, a non-linear space, we'll be working with this type of structure, a vector space. So let me go straight to give the following definition of one of the spaces that we'll be looking at in this course. And that has to do with non-linear spaces. Okay, non-linear spaces. So let's define what we mean by that. Non-linear spaces, non-linear spaces. Non spaces. Okay. So of course, definition is very key in pure mathematics. So let X be a linear space or a vector space. You know, they are the same thing, linear space or a vector space. So that's the structure. And of course, you usually define a linear space or a vector space over a field. Okay, over a field, over a scalar field, over a scalar field. Usually the scalar field is either K or R or C. Okay, but you generally we call it K, which could be either R or C. I'm sure you know this set. This is the set of real numbers. This is the set we basically studied in the first course, which is real analysis. Okay, so this is the structure of is a field, is a field, or the C, the complex numbers, which is a generalization of this. So usually our vector space is defined either these two field structures, either R or C. Okay, which is this is the set of real number, the set uh, um, of complex number. So what do we now mean by a norm over this a norm on X or a norm on a vector space. So we define as follows. So a norm on X, which is a vector space, is a is a real valued function. It's a real valued function. Usually in mathematics, if you mention function, you tell us the domain and the range. So it's a function. Let me denote it. The symbol is like this. You have two verticals on the left, and then these dots represent some vector structures. Okay. Then another two vertical line on the right. So when you see this notation or this symbol, it means none. Okay. And is a function, of course, is a function defined on vector x, vector space x, and the range, okay, is 0 comma infinity. Okay, 0 comma infinity. I'm sure you know this is closed on the left, while open on the right, because you are talking of distant function. Okay, between 0 and infinity. Does not distance, you cannot tell us distances are negative. So the range is what we call R positive, if you like. That's what we call this set, R positive. Okay. So, and this norm or this function satisfies certain axiom. So, which satisfies certain axiom, which satisfies the following axioms, the following axioms. Okay, the following axioms. What are the axioms? Maybe I share this into two. Number one, which we call N1, that's the first axiom, is that, of course, distance is non-negative. In other words, the norm of any vector x will be zero. Norm of any vector s will be zero. And of course, that norm is zero, and that will happen if and only if and only if you have that zero x is a zero vector. Okay, and this will happen for all x in, of course, the domain of your function is x. Okay, that's n1. N2 is that the norm of a kx, okay, uh, is equal to the modulus of k norm of x. I think I need to share another slide. I want to just remember all these definitions. I want to state these axioms. There are just about three of them. The way I'm writing it here is not all that clear because of want of space. So I need to write clearly so that, because you just have
Okay.
to remember the axioms. Yes, go
So,
ahead.
what is the first? I mean, after the real valid function, what's the next step? X, the norm defines in zero infinity.
Yes, okay, okay. It's a real valued function. This is norm. Norm, norm as per this word norm, norm. But I use notation. This notation is referred to as norm. Two
Okay.
vertical lines on the left, then your vector inside, then two. So instead of writing this, of course, in your book, I'm sure if you are reading the research articles, you would have been seeing symbols or notations like it. It means norm. Okay, and is a
Okay.
function with the domain as the vector space. Okay, and your range is a distance function, of course. You are measuring the distance of a vector from the origin. Of course, if you recall, this is your x and y axis, x and y axis. This is the origin. So if, for example, my x is here, I'll be interested in the distance between the x from the origin. That's exactly what we mean by norm of x. Okay, or maybe there's a vector y here. You'll be interested in measuring the distance of this vector from the origin. That's norm of y. Okay, and those norm of y, for you to say that this is a norm, it must satisfy certain axioms. I'm saying I want to share a new slide. This place, I'm not really, is so clumsy because of want of space. So let me share a new slide so that I'll be able to write my axiom. There are three of them that must be satisfied before you claim that this is a norm on X. Okay? So let me share a new slide so I can do a very neat work regarding the listing of all the axioms that must be satisfied. So let me share a new slide now right away. Okay, so as I said, if you say that x from r, x, your norm, which is a function, from x, which is a vector space, to the range is 0, infinity, okay, which some authors may call r plus, okay, which is so this is a norm. It's a norm on x if the following axioms are satisfied. If the following axioms are satisfied. The first axiom, we call it N1. Okay, N1. N1. The first axiom is N1. And that axiom is saying that norm of x is equal to norm of x is 0. Okay, if and only if x is a 0 vector. Okay, and this will happen for every vector x in your domain of the norm or domain of the function, which is capital X, the vector space. That's the first axiom. The second axiom, which we call N2, is that if you pick up, because you define this norm over a k, you define this vector x over a k, which we say is usually R or C. So, or C. Because this field, I can pick up a scalar from them, okay, either from here or here. Of course, you can pick up a scalar. So if you pick up k, your k, small letter k, as your scalar from this field, and then you do the norm of such a k with any vector x, you discover that the value of such norm kx will simply be the modulus, which is the length of such vector, dot norm of norm of vector x. Okay, this will happen for all vector x in your x, and of course, it will happen also for all k in capital K. Capital K is any of your R or C usually. Okay, any of your R or C. Okay, the last entry is what we call the famous triangle inequality. In other words, if you have norm of x plus y, this will be less than or equal to norm of x plus norm of y. Okay, I don't know if you can see it very well. Let me write here. Entry, norm of x plus y, norm of x plus y. This is less than or equal to norm of x plus norm of y. I just want to be as clear as possible. Okay, this will happen for all vectors x, y in the linear space X. Okay, so if these three axioms, N1, N2, and N3 are satisfied, okay, if N1 to N3 are satisfied, we now say that this norm, this vector space X, together with the norm, this norm, together with that norm, is called a normed linear space. It's called a normed linear space. Okay, it's called a normed linear space. Okay, so if you hear a normed linear space, we are saying that what you're talking about is you have a linear space X or a vector space X together with a norm. There are several types of norm. We are going to see a series of examples of norm on linear spaces. Okay, so but once you hear a normed linear space, what we are saying is that you have a vector space that a norm is defined on it. Norm means that function from your vector space to, of course, 0, infinity, norm positive, positive R plus, such that N1, N2, N3 axioms are all satisfied. Okay, So that's what we mean by a nonlinear space. Now, there are several examples. I'm sure we have already encountered many of them, and maybe even without knowing it. So let me share a new slide, and then we proceed. Okay, so okay, so we proceed by looking at examples. We just define what a norm is. So can you produce concrete examples of what you mean by a norm? Example. Okay, so let me have example. Uh, Example number one. Okay. Uh, let your vector space, let X be defined. Let me divide this into two like this. So let X be R2. I'm sure you know R2. That's at R2. Of course, what do you mean by that? If you pick a vector from R2, how does it look like? If you pick a vector, for example, for arbitrarily vector X bar in R2, how does it look like? That X2, you have X1 is two-dimensional. So you have X1, X2. So if you pick up any point from this set, is simply it's just like when you draw your X and Y as this graph. If you pick up any point, that point is completely described by the X comma Y coordinate. So because that's R2. Okay, so if you now define, how do you define distance in R2? Okay, look at the way I want to define that norm, because that distance is the norm. So I'm saying that if that norm in R2, let me call it norm 2. Okay, norm 2. Of course, the range is a function. Beginning, the domain is R2. Okay, and the range obviously, like we usually say, is 0 comma infinity. Okay, the norm itself is defined as follows: norm norm of X bar, because this X bar, as we said, is from R2. So norm of X bar, and we call it norm 2. We said that we are defining it as follows. It's going to be equal to X1 squared, because if you pick X bar from R2, is that X bar is simply X1, X2. So you have X1 squared plus X2 squared, X2 squared to power half, everything to power half. That's how I'm defining that norm. Okay, that's how I'm defining that norm. My claim is that my claim is that norm 2, so defined, norm 2 is a norm, is a norm, is a norm on R2. Well, before I'm going to verify this one, I'm going to verify it, but let me start with something simpler. Okay, when I do that, then I will now come to verify this one. Okay, because I'm working on R2. Okay, let me work on R1 first. That's more simpler, and that will make more meaning to you before I will come and do this one. Okay, let me work on R1. Look at this example. Example, if you have your norm, instead of your norm, your X being R2, let me pick only R1. So R1, okay? And of course, if you pick X, it's just like that, the real line, like we studied in real analysis. So let me define norm 1. The one we have here is norm 2. So let me define norm 1 as follows. Norm 1 is simply the absolute value function, okay? Okay. So that function, and of course, your k, let's have this X defined over your k. Let's capital K, let it be also R. Okay. So we now claim that this is a norm. My claim is that norm one is a norm on R1. Okay. on R1 on R. Verification, well, if you claim it's a norm, it means that the three axioms N1, N2, up to N3 are all satisfied. Okay, so verification. Let's now verify verification. Okay, N1, N1. Who can remind us N1? What's N1? Axiom N1. What does it say? Somebody should tell us. What does N1 say?
Norm of x is equal to 0 if and only if x is equal to 0.
Good. Norm of x, with our norm in this case, norm 1 is norm of x, right? Is equal to absolute value of x. So norm of x, which is equal to absolute value of x, is equal to 0 if and only if, this is the notation for if and only if and only if you are dealing with a zero function. Okay, we need to verify this. We need to verify this. Now, let me share a new slide. The verification is very simple. Let me just share a new slide. And then, of course, if you record the definition of absolute value function, your job is done. I'm sure we dealt with absolute value function in reanalysis. So you will not have, so you can now see why I have to take reanalysis first before taking function analysis. And after taking function analysis, the last course will be measure theory. So you see how we lined up those courses like that, because you have to do reanalysis before function analysis, then function analysis before measure theory. Okay, this one is well known to us from our knowledge of the first course, reanalysis. So if you understand that definition of absolute value function, this will not be difficult to show. But let me share the next slide so we can conclude showing that. Okay. So we are saying that norm, which is norm of x, norm 1 is simply, we are trying to actually show N1. So which norm 1 is absolute value function. Of course, absolute value function. What do we know about this function? This function is always greater than or equal to 0. Is it not? For all x in x. That's one thing we know about the absolute value function. As a matter of fact, norm of x equal to 0 if and only if you are dealing with a zero vector. Why? That's simply by definition, norm of x which is equal to absolute value of x is equal to 0 if and only if you are dealing with a zero vector. How? By definition of the absolute value function. By definition of the absolute value function, from our reanalysis, this can never be 0 except you are dealing with a zero vector. Okay, so this satisfying axiom 1, satisfying axiom N1. So you have verified axiom N1. The next job you need to do is to verify N2. Norm x1 is equal to the absolute value of norm of x. Anyway, for N2, you are dealing with kx. You're picking up a scalar k from the scalar field, which is R. Okay, you're also picking up your x from the set x, which is R also. So if you now have norm kx, which will be absolute value of k norm of x, k norm of x, right? And norm of x is the absolute value. K norm of x is absolute value of kx, right? An absolute value of kx. What does absolute value function do? Absolute value function makes a function to be positive. A scalar to be positive, right? So that, and what denotes that positivity is the modulus of k. Okay, norm of x, absolute value of x. So absolute value of kx is equal to absolute value of k, absolute value of x. Okay, so verifying N2, because N2 says that norm of kx, okay, must be equal to modulus of k norm of x. Is it not? So that's exactly what you have done by this. So you now see that absolute value of k modulus of k norm of x is equal to absolute value of k, absolute value of x. So that actually verify N2. Now, the last one, N3, is that what? Norm of x plus y. I'm sure you know this is exactly what we want to do. Is actually equal to absolute value of x plus y, right? Absolute value. And this absolute value satisfies triangle inequality. This is less than what? Or equal to absolute value of x plus
Absolute value of
absolute
y.
value of y. Is it
So this
not?
is the
What is
simplest.
this? What
Yeah.
is that? This
That
is
one is
simply
norm of
norm
x
x,
plus norm of
yes,
y.
plus norm of y. Is it not? Is it
So
not?
now it's
So
okay.
you now see that N3 is also what? Satisfied. So you have simply shown that N1 is satisfied, N1 is satisfied, N2 is satisfied, N3 is also satisfied. So what's your conclusion about the norm? Is it a norm? It
And
then
one is a
means
normal
that
space.
the x together with norm 1, which is absolute value of norm 1, is a norm on R, is a norm on R, on R. So it's a norm on R. Okay? Because N1, N2, N3 are satisfied. So it's a norm on R. Okay? So that's good. We just shown a norm using a R1. Let's now share a slide. We now go back to the other example that has to do with R2. I deliberately did this one because this one is simpler. So you make meaning of the second one now. So let's proceed with the third one. Okay. So I have the following. If you recall the other example that we dropped, that example, what do you have? That example is in R2. If you recall, your X is R2, okay? And you are talking of norm2, your norm2 uh, is defined as follows. Norm2 of X is defined as x1 squared plus x2 squared raised to power half. That's exactly how that norm is defined. So you want to show that this norm 2 is a norm. First of all, you look at N1, whether assume N1 is satisfied. And assume N1 is, you need to show that norm x2 is equal to 0 if and only if you are dealing with a 0 vector. I think that's what you must show, right? Aha. So you now see that norm x2, norm 2, how is it defined? It's defined as x1 squared plus x2 squared, everything to power half. Now, this is equal to 0 if and only if the whole of this is 0. In other words, if and only if x1 squared, let me put it here. If and only if and only if x1 squared plus x2 squared is equal to 0. Well, this will be equal to 0 if and only if x1 plus x2 equal to 0. Okay? This will be equal to 0 if and only if x1 equal to x2 equal to 0. And this will be equal to 0 if and only if x bar is equal to 0. Okay? So what have you shown? You have just simply shown that, you've shown that norm 2, which is norm x2 bar, as defined here, is equal to 0 if and only if you are dealing with a 0 vector. Okay, so this satisfies axiom 1, satisfies axiom N1. Okay, I don't know if you understand the verification. Okay, look at this vector squared, another vector squared. To power half means the square root of that, right? That's the meaning of that. To power half, that's the square root. And this whole of this, the whole of this will be 0 if and only if you have that x1 plus x2 will be 0. Because if you say that the square root of something is 0, that means what is inside, the addition of what is inside is 0, right? And if this addition squared is 0, it then means you are talking of 0 squared plus 0, meaning that x1 plus x2 is also equal to 0. And for x1 to be 0, x1 plus x2 to be 0, it then means that x1 and x2 are equal, and then x bar is equal to 0. So that's, in other words, your x bar completely can be described as 0, 0, which is the origin. Okay, so that's exactly what that x bar looks like. So that's exactly what N1, axiom N1 is saying. That's what axiom N1 is saying. Okay, so the next we need to define is axiom N2. Axiom N2. Please do send another message across in your WhatsApp platform to your colleagues. Maybe they will see it again and they join the class. Please, you can do that. Send another message across to your colleagues in your WhatsApp. So we've just shown N1, so I need to show N2. N2. N2 says that you have norm x bar 2, norm 2, which is k. I'm sure you remember that k must be there first. K norm of x. In other words, norm of k x bar norm 2, which is equal to, if you recall, this will be k x1 squared plus k x2 squared, everything to power half. I'm sure you know that's how it is, right? If you do k norm of x1 bar, that would be k x1 squared plus k x2 squared to power half. That's how that norm 2 is defined. So this will be the same thing as, if you like, k is here, and it's all squared. So you can talk about k squared, okay, into x1 squared plus x2 squared, okay, everything to power half. Okay, look at this. K squared to power half can never be negative, K squared, the half, we take away the 2. Okay, these two. But one thing we know is that is a square root of an object, so it can never be negative. So you'll be talking of something like absolute value of k, okay, into x1 squared plus x2 squared, okay, everything to power half. What is this? This is simply modulus of k norm of x. This one here is norm of x bar. Norm of x bar, norm 2. So you have just shown that k norm of x bar, which is norm 2, is equal to modulus of k norm of x2 bar. What is this axiom? What is this axiom? Somebody should talk. What is that axiom? This is N2 now.
N2, yeah.
Satisfying N2, right? That's what N2 says. Okay, N2 says that this must be equal to this. Is it not? The norm of kx bar must be equal to modulus of k norm of x bar. Is it not? That's norm 2. So that's exactly what we have just shown. So the next one now is the triangle inequality, which is to show that num x bar plus y bar, okay, num x bar plus y bar, okay, must be less than or equal to num x bar plus num y bar. Okay, so this is what we must verify in num 3. Okay, I'm going to share a new slide for us to actually look at that triangle inequality. Okay, so once we've done N1, we've done N2. If we show this one now, if we show if we show N3, then our job will be done. We now conclude that that num2 as defined is a num on R2 but let's now verify N3 now. So I share a new slide so we can proceed. Okay. Okay, so I proceed to show N3. Well, I can do the following. I can do the following norm of x bar plus y bar, of course, is norm 2, you know. Let me do square. I'm sure you recall what norm x bar is. If you do square, that half on the right will go. Okay, that half on the right will go. So this will be equal to norm. These are vectors. You know, vectors, you add vectors component wise. I'm sure you've done courses in in linear algebra. So if you are to add vectors, let me first of all do this. Maybe just to remind us how to add vector. If you say x bar is in R2, y bar is in R2, and you have to add them, what do you mean? You are saying x bar there is from R2, so you have x1 comma x2. Okay, then plus y bar, you also have, it's also in R2, so you have y1 comma y2. So if you have to add them, how do you add them? It will be first component of the first vector plus the first component of the second vector, which is x1 plus y1. Okay, then comma, because it's a vector in R2. When you add two vectors in R2, it's also going to be in R2. So the second vector is the second component should be added to the second component also, so which is x2 plus y2. So I'm sure you recall this rule. So that's how we are going to, when we are doing this is exactly what we mean. Okay, so in other words, this will be equal to norm of x1 plus y1 plus y1 and x2 plus y2. Okay, so we know this clearly. And this is simply num2 squared. Okay, num2 squared. And I'm sure you know how we add this. This is equal to summation I running from 1 to 2 of because you have this like x1 y1. So I have xi plus yi all squared. Okay, all squared. Okay, and of course, this xi plus yi squared, you can open this bracket, this square. If you open up the bracket, what do you have? You have the following summation I running from 1 to 2 of this will be x squared plus y squared plus 2xi, so which has xi squared plus 2xi yi plus yi squared. Okay. Of course, this will be, the whole of this will be less than or equal to summation. You can break it up now. You can break it this. So you can break up. So you have summation I running from 1 to 2 of xi squared, xi squared plus 2, because this sum is not affected by this 2 is a scalar, so I can bring it out. Summation I running from 1 to 2 of xi of xi yi, this one. I'm putting absolute value. That's why this less than or equal to is there. Okay, now plus the last component, which is this one, plus summation I running from 1 to 2 of yi squared, Okay, now this candidate is not easy to resolve. This particular one, this candidate here, okay, for me to resolve, because already I know this candidate, the one I need to resolve is this one. And there's a famous inequality which is known as Cauchy-Schwarz inequality. We are going to prove it towards the end of this course, but that's what we are going to, is a result. It's known as Cauchy-Schwarz inequality. It's actually a general, a sort of a corollary to a more general theory, which we call Holder's inequality. Okay, we are going to see both Holder's inequality and Cauchy-Schwarz inequality towards the end of the course. Okay, but then we simply, what we need to do is to use this Cauchy-Schwarz inequality to resolve this one. And what does Cauchy-Schwarz inequality say? Cauchy-Schwarz inequality say, when you see this type of object, look at how to resolve it. It states the following. If you have summation I running from 1 to 2, okay, of for Holder's inequality will run to infinity. So, but this Cauchy-Schwarz is just a corollary of that. So he's telling you that if you have such of xi, yi, this is less than or equal to, summation I running from 1 to 2, okay? I running from 1 to n. That's generally so, but you can take to I running from 1 to n, I running from 1 to n. So my n is 2 in this particular case, okay? Of absolute value of xi squared, to power half, and then you do the same thing on the y component. As summation I running from 1 to n, okay, of yi squared to everything to power half. So this which we have encountered here, we now replace it with this. If you replace it with this, your job is done. You just take note of this, and then your job is done. I want you to look at this. I'm going to share a new slide and replace the whole of this with this Cauchy-Schwarz inequality. And then once I replace that, and we make a little observation, and we now conclude proving the triangle. Don't forget where we're going to. We want to prove triangle inequality for this. Okay? So, but then we encounter this challenge, but we record that we can use Cauchy-Schwarz inequality, which is this, replace it, and then we can easily conclude. Okay? So let me share a new slide and then substitute this inside this place, and then you see that the next line, our job is done. So let me share a new slide. If I share that slide and substitute with my Cauchy-Schwarz inequality, my job will be good as done. Look at this, where I am. I have norm of x bar plus y bar. Of course, we are dealing with norm 2. We have just said before that Cauchy-Schwarz inequality, I just want to recall the last inequality we said. We've said that this is less than or equal to summation I running from 1 to 2 of xi squared plus 2 summation I running from 1 to 2 of the modulus of xi, yi, plus the last one. Last time is summation I running from 1 to 2 of yi squared. And this candidate is what we have issues with. But we want to substitute with the Cauchy-Schwarz inequality. So if you do that, you have the following. Summation is less than or equal to, this candidate is there. I recall it back. I running from 1 to 2 of xi squared plus this candidate now is 2. Instead of this Cauchy-Schwarz inequality, I should replace with the following. Summation I running from 1 to 2 of xi squared, all of these to power half. Also summation I running from 1 to 2 of yi squared, all of this as well to power half. That's exactly then plus this time. This is for this plus the last time is summation I running from 1 to 2 of the last time, which is yi squared. Okay? So this looks like something I already know. If, for example, I pick up my A to be this candidate, this candidate, which is a summation I running from 1 to 2 of xi squared to power half, okay, to power half. And then I pick my Y to be the other candidate, my B rather, to be the other candidate, which is summation I running from 1 to 2 of yi squared to power half. What's your observation of that? Well, you simply see that the whole of this candidate looks as follows. It looks like norm of x bar plus y bar, okay, norm 2, of course, norm 2 squared is less than or equal to, because you see that this candidate is like my A, this candidate is like my B. If that is the case, and you express something like this, something like a plus b squared, the whole of this will look like a plus b squared. If you open this bracket, if this is your a and this is your b, if you open that bracket, you get the whole of this. Okay? So which is equal to what is this one? This is num 2. This is num x bar for this A. A is this one. And what is that? That's num x2. Num x2, num 2. Plus, what is this B? Which is this one? What is this B? This num y. Num y. Okay? So what have you done? You have just seen that num 2 num x bar plus y bar squared is equal to this. So if you square both sides, if you find the square root of both sides, what do you have? If you find the square root of both sides, you are back to verifying the fact that num x bar, that is num x bar plus y bar, of course, num 2, is less than or equal to, I'm going to write at the other side. I don't want to go to another screen. It's less than or equal to num x, this num 2, of course, plus this x bar, I'm sure you know, plus num y2, num y bar. Look at this. This less than or equal to this. This triangle inequality now, right? Verifying N3. Is it not? I hope you are following what we are doing.
Sure, I'm following.
Yeah. Okay. So this triangle inequality. So you've just seen that N1 to N3 is satisfied. So it then means that that set, the set which is R2, together with num 2 is a norm. So since N1 to N3 are satisfied. So since N1 axiom N1 to N3 are satisfied, it follows that this structure, which is R2, that's my X, together with the norm itself is norm 2. Okay, is a normed linear space. It's a non-linear space defined on R2. Okay, so that's our conclusion over there. We are going to give, there are several examples. The more example we give, the better understanding of this structure called nonlinear space. The next example I'll be giving, I want to build linear spaces. One of the linear spaces or norm spaces that is very common is the small LP spaces. or what we call the sequence spaces. So let me first of all define the sequence spaces. Very beautiful spaces, a whole lot of things. Norm can be defined on sequence spaces. But then, first of all, let's define to show that define what that LP is all about. That small LP. Okay. I call that an example also. Okay. And as I said, I'm interested. The spaces they call this sequence spaces. Sequence spaces. We've studied sequences in real numbers, so it's not far away from that. And the space itself is usually denoted as follows. The space LP, LP, LP. And of course, what's P? P is a number ranging between 1 and infinity. It can include infinity. We will study, but for now, we will leave alone the L infinity. We will study L infinity. L infinity is simply the space of all bounded sequences. I'm sure that's not strange to you. If you've done reanalysis, you know what we mean by saying that a space or a sequence is bounded. So if you collect the space of all bounded sequences, that's L infinity. We'll keep that one aside. We're going to specially study that. Okay. So, but for LP, how do we define that? Of course, we can define LP over your vector space R or vector space C. But let's just look at the one over R. Okay. This is defined as follows. Of course, it's a vector. If you pick up an X bar, it's a vector infinite space. It's an infinite dimensional. Okay. So if you pick up X bar, how does it look like? Well, it's just a sequence space. You have the first term of the sequence, the second term, the third term, and you never can finish. It's infinite dimensional. Okay. So X1, X2, X3. And of course, is such that this is such that each of your xi are actually real value because you are dealing with the real. So each of your xi belongs to the real number system, and it's such that if you claim that this sequence belongs to LP, what you are simply saying is that the summation I counting from 1 because it doesn't finish. I from 1 to infinity. I counting from 1 to infinity of each of the modulus of each of your xi, okay, to power p, because there is LP. So to power p must be summable, must be less than infinity, must be summable. So that's the space. Okay, the space is such that if, for example, if my p, because p could be any number between 1 and less than infinity. Take, for example, if I'm looking at LP2, let's say my P is 2, okay? Oh, sorry, L2, L2R, okay? That's my P is 2. How does it look like? You are simply talking about the space X bar, okay, such that you have, of course, the sequences are infinite dimensional. It does not finish, such that all your Xi belongs to R, and such that the summation I counting from 1 to infinity of the modulus of all the Xi, P is 2, L2 to power 2, okay, must be less than infinity. This is the space of L2 space. Okay, L2 spaces. Okay. So this space is a linear space. Is a linear space. Of course, if you claim that a structure is a linear space, you must have plus and dot. In other words, you have the addition, vector addition, and scalar multiplication. Okay, define. Let's define vector addition and scalar multiplication as follows. I'm not going to do the whole of nine verification to show that it's a vector space. Maybe I'll leave you that for you to do as an assignment. But then let me just define vector addition and scalar multiplication. Then I will now leave it for you to show all the axioms of vector space, okay, to show that it's satisfied. So, of course, for pick up two vectors, for example, if you pick up x as a vector, if you pick up x, it's infinite dimensional. So you have x1, x2, x3, and so on and so forth. If you pick up another vector y by, it's also infinite dimensional, y1, y2, y3, y4, it doesn't stop, infinite dimension. Okay, these are arbitrarily vectors, in LP. Okay, in LP. And of course, how do you add vectors? I've already taught us how to add vectors. Vector addition, x bar plus y bar. You add vectors component wise. So it's simply x1 plus y1, comma, x2 plus y2, x3 plus y3. That's how we add vector component wise. You never can finish because each of the vectors are infinite dimension. But then at least we know how to add them. We can add them. Okay. And also scalar multiplication. So for arbitrarily vector, for arbitrarily scalar, because this is a vector space, you define it over a field. For arbitrarily scalar, okay, arbitrarily scalar lambda, okay, you have that you define scalar multiplication as follows. Lambda x bar um, is simply lambda x1, comma, lambda x2, comma, lambda x3, comma, lambda, and so on and so forth. So that's how we do scalar multiplication. With this vector addition and scalar multiplication, I claim that LP is a linear space or a vector space. It's a linear space. Verification, I said I will leave that as an assignment. Please, you copy it. You submit it to me. I want you to show that this is a vector space. Please, you need to do this assignment because, this space, we will study this space in details in the future. We are going to build a whole lot of norm on it. Of course, you don't build a norm on something that is not a vector space. So the more you work to verify this, the better understanding you will have. So that when we begin to build norm on these sequence spaces, you will not have issues with that. So I've defined my scalar vector addition. I've also defined my scalar multiplication. Of course, the challenge you need to do is to show that this LP together with the addition is an abelian group. And the LP together with the dot, that's scalar multiplication, all the LDL, left distributive law, right distributive law, existence of a one, that is an identity element, a multiplicative identity element, and so on. So you show all those axioms, field axioms, and then your job is done. So the verification, I'll leave that for you as an exercise. Okay, so I want to pick up some sequences to show whether they belong to sequence space or not. Okay, I pick up some sequences to show whether, for instance, whether they belong to the space L1 or space L2 and so on and so forth. So that's a nice job. Okay, so I proceed as follows. Okay, another example. Another example. Look at this. Consider the space L1, which is defined as follows: X, which of course is infinite dimensional. You have X1, X2, and so on, is infinite dimensional. Okay, infinite dimensional, such that all your Xi, they are R-valued. And of course, the summation I counting from 1 to infinity, and the modulus of all the because it's L1, so it's the whole of this to power 1 is less than infinity. Okay, So I pick up these sequences and ask myself whether there are elements in this space. I pick up the first one. The first one is a space, is a sequence like this one, X, which is equal to a sequence we already know, which is 1 over n, which is the first term is 1, second 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so on and so forth. Now, my question is, this sequence, is it in L1? Is in the L1? Well, we are going to verify that. Let me pick another sequence. Okay. Let's see. Let's answer this one first before we pick another one. Well, for this space, for this sequence to be in L1, for this sequence to be in L1, it must follow that if you put in this sequence inside this, it must be summable. That's convergence. So, but of course, if you do so, you have the following. It follows that if you put them inside, you have summation xi, which is equal to summation, which is equal to summation of all of this, which is 1 plus 1 over 2 plus 1 over 3 plus so on and so forth, right? This sequence is familiar to us. This is equal to summation 1 over n, if you recall. And in our reanalysis, we tested the convergence or otherwise of this sequence. Is this sequence convergent from your test of series convergent in reanalysis? Is it convergent? I want you to answer. We've already seen this sequence now in reanalysis. Is it convergent? This is a sequence P series, belong to
No,
P series with P equal to 1. Is it convergent?
no, it's not convergence, it's harmonic.
This sequence diverges. Yeah, you are correct. This sequence diverges. We've already seen it in our reanalysis. This sequence diverges by P series test. We studied this sequence in details. So it diverges. Okay. And if it diverges, then it doesn't belong there. It doesn't belong to the space because every sequence in this space must converge, must be less than infinity. This one diverges. This one approaches infinity as n goes to infinity. As n goes to infinity. So it diverges. It doesn't belong here. So this sequence is not an element. It follows that X does not belong to L1. Okay, it doesn't belong there because of the definition. So that's one. Let's look at another one, B. I'll give another sequence. Let's see whether it belongs to L1. The B, another sequence. I have the following sequence. The sequence xn equal to 1 over n squared plus 1. Okay, of course, your n is the entire natural number system, which is 1, 2, 3, and so on. Okay, so my question is, this sequence is xn an element in L1? Well, if it's an element, it will follow that L1 R, which is defined as the set of S infinite dimensional, X2, and so on and so forth. Each of your Xi belongs to R, and such that the modulus Xi is less than infinity. Okay, so if I do this, the modulus summation 1 over n squared plus 1, okay, this candidate is strictly less than, if you recall, this series, we've done series like this. This is less than summation 1 over n squared. We know this candidate already. This is a P series with P equal to 2. Is this series convergent? Is this series convergent from your reanalysis knowledge? Is it convergent?
Yes, it's
This
convergent.
candidate, we've seen this is convergent. It is
Yeah,
convergent, in other words, convergent by P series test. That
exactly.
is summation 1 over n squared is less than infinity. So it belongs to L1. That's exactly what L1 say, that it must be convergent. It must be less than infinity to belong there. In other words, this sequence Xn is an object in L1. So the first A does not belong to L1, but this second one, it belongs to L1. Okay, let's look at L2. Let's look at L2. We define, you see, we are looking at this sequence space. We want to have a good understanding of the sequence space. As I said, it's one of the important space in functional analysis. It's one of the important spaces. So that's why we are taking our time to look at them. And of course, we've seen that LP also is a vector space. I stated it, I defined vector addition and scalar multiplication, but I've allowed you to go home to show really that it is a vector space. So, but then let's look at L2. We've done a lot of two examples on L1. So let's pick up L2. Another example. Okay, so let X equal to L2 space, the sequence space L2. Of course, how is it defined? If you pick up X in L2, you are simply, each of your vector is infinite dimensional. So you have X1, X2, X3, and so on. It does not stop. And it's such that each of the component vector belongs to R. Okay, they are all R values. And it's such that the summation, because you are in L2 now, the summation of all of those, summation of your X to power 2 must be summable, okay, must be convergent. That's the criteria. So that's how my X2 is defined. Look at this sequence. X equal to 1, 1 over 2, 1 over 3, and so on. We've seen this candidate before when we were in L1. My question is this same candidate, this question A, which is not in L1. Okay, so let me ask myself, is it in L2? It wasn't in, we've shown that it's not in L1. Okay, but is it in L2? Is X in L2? We've shown that it's not in L1, but let's find out whether it's also in L2. Well, if it's going to be in L2, this must be satisfied. If it's going to be in L2, so if you now do summation 1 over, because n, this candidate, 1 is known as 1 over n. An object in L2 is to power 2. So this to power 2. So this becomes summation 1 over n squared, 1 over n squared. We know this candidate. What happens? Is this convergent or not?
Convergent.
If this is convergent, this is less than infinity is convergent. Hence, the conclusion is that this same X belongs to L2. It wasn't in L1. It was not in L1. We show so, but the same candidate the same sequence that is not in L1 belongs to L2. Okay. So let's look at the other example that was in L1 to also ask whether it's in L2. It's good to look at ask some of these questions. We've seen the B sequence, the sequence B was in L1. So we're asking ourselves, is it also in L2? That's the second part of this question. So look at that B, if you remember that B sequence. The B sequence, if you remember, looks like this one. Your Xn looks like what? 1 over n squared plus 1, if you remember. Okay, is this sequence, is X in L2? We showed that this one is in L1. We are now asking whether it's in L2. Well, For it to be in L2, it must follow that 1 over summation of x, okay, to power 2 must be finite. Okay, so if you now do this, you have summation of 1 over the sequence itself is n squared plus 1 to power 2 because you are in L2. Okay, obviously, by this candidate is less than summation 1 over n counting from 1 to infinity of 1 over n4. If you remember, this is by comparison test, test of series. Now, the question is this is less than this. This candidate, is it convergent or not? This series, is it convergent or not?
I think it's convergent.
It's convergent, exactly. This is convergent by P, because P says if P is greater than or equal to 1, greater than 1 rather, it converges. P, so this is convergent. So meaning that it follows that this sequence is in L2. So you see that all sequences in L1 is in L2, but the converse is not true. Okay, so what have we shown? I'm just trying to make some remark on those two examples. From those two examples, we've shown that if x is in L1, it follows that x is also in L2. But we have shown that there exists some x in L2 such that x is not in L1. From those examples, we've seen that every sequence in L1 is also in L2. But we've seen a sequence which is not, which is in L2, but that sequence is not in L1. Okay? So that remark is very important. If that remark will make us to formulate a proposition. But before we get to that proposition, let me look at the other space, which I said that we will study separately. Recall that we just studied the LP spaces, P without infinity. Okay, P without infinity. Now let's look at P being exactly infinity. P being exactly infinity. That's L infinity. So let's see what that it is. Let me share a new slide. We now give that example of space, sequence space. Another example. Okay, this space L infinity. Okay, that space L infinity is defined as follows. They are sequence space, of course, and each of your sequence is infinite dimensional. X1, X2, X3, you never can stop. Of course, each of your Xi, they are R valued, and is such that this X bar is bounded. That's that space. That is, L infinity is the set of all bounded sequences. Okay, I'm sure you remember when we say that a sequence is bounded. Xn bounded. What does that mean? A sequence is bounded. What does that mean? Have we forgotten? I hope you are still there.
Yes, sir.
Yeah. When do we say that a sequence is bounded?
When it is bounded, a bounded sequence is one that is Bounded above and below.
Below, yes. What do you mean by bounded above? What do you mean by bounded below?
Um,
Bounded above, that's one. Two, bounded below. What's the meaning of that? Bounded above, what does that mean? There exists a K
There exists beta.
such that,
There exists such that for
okay,
all x
uh-huh.
on elements of x is less than beta, less than or equal to beta.
No, say it again.
There exists beta such that
Okay.
for x is less than or equal to beta for all x and
X.
elements of the set, or x minus epsilon naught is less than something beta.
Okay, okay, okay. I understand what you are trying to say. Well, you recall also, instead of even talking of lower and upper bound, I can just say that there exists a K greater than 0 such that the absolute value of Xn, absolute value of Sn is less than or equal to K. Okay,
Yeah.
that takes care of both the lower bound and upper bound. Okay, that's the shortest way of defining boundedness. So this space is the space of bounded sequences. The space of bounded L infinity is space of unbounded sequences. Okay, so like as I said, from that last observation, we've seen sequences in L1. Every sequence in L1 is in L2, but the converse is not true. That will now lead us to formulating a proposition. Okay, so let's go to the next slide so we can do so. We can now formulate that proposition. Okay, so I have proposition if 1 is less than or equal to P, less than or equal, we are even including the L infinity, less than or equal to plus infinity. Okay, then you have that LP, okay, is a subset of LQ. In other words, just like L1 is less than or equal to L2, it follows that L1 is a subset of L2. So that's what that proposition is saying. Okay? So in other words, you can say that L1 will be a subset of L2 because P is 1 is less than or equal to 2. So L3, for instance, will be a subset of L4, and so on and so forth. So that's what this proposition is trying to show. The proof is, you see that also everywhere. Okay, so we try to, since we have shown that LP is is a linear space or a vector space, we can begin to define norm on it, because in every vector space, you can actually impose a norm on vector space. So let's do so now by imposing norm on LP spaces. So I will now share a new slide to give such an example. Okay, example. The function let's no, second. Now, the function um, defined as follows: norm from LP we just discussed. You have 0, infinity. That function defined as follows: defined by norm of S bar. That norm is the norm of an LP, and we're defining it as summation I running from 1 to infinity of xi to power p raised to power 1 over p. This will happen for arbitrarily x, for x bar, which of course is infinite dimensional, x1, x2, x3, and so on. Okay, and these are vectors in LP. Okay, we are saying that this function is a norm on LP, small LP. Of course, your P is between 1 and infinity. We don't include infinity. We have L infinity, okay, separately. Okay. Of course, you can show that this is a norm. You can show that this is a norm. N1, N2 would be easy to show, but for you to show N3, which has to do with triangle inequality, you will encounter, obviously, just like when we are in L2 or R2, we encounter the Cauchy-Schwarz inequality. In this case, you will encounter Holder's inequality for you to verify the triangle inequality. So I'll do L1, I'll do N1, N2, and then I will give you N3. Since I have already done similar verification for R2, you will also submit that as an assignment next class. So I will do N1, N2, and then I will give you N3. That will involve Holder's inequality. I will just state the Holder's inequality. I use it exactly the way I used that Cauchy-Schwarz inequality, and then the job will be done. But let me verify. This is actually what we want to verify. This is a norm. If this is a norm, means that axiom N1, axiom N2, and also axiom N3, all of them must be satisfied. So let's share a new slide and then we begin to do the job. Okay, that's fine. Now, if it's a norm LP is a norm if N1 to N3 are satisfied. Okay. For N1, you have that N norm of X, L infinity is defined as summation I counting from 1 to infinity of xi to power p raised to power 1 over p. You see that this will be equal to 0 if this will be equal to 0 if and only if summation I counting from 1 to infinity of xi to power p is equal to 0, and this will be equal to 0 if and only if x1 plus x2 plus x3 and so on and so forth is equal to 0. And this will be equal to 0 if and only if x is a 0 vector. And this is exactly what N1 says, satisfying N1. Satisfying N1. Satisfying N1. So we've verified N1 that norm of x is equal to 0 if and only if you are dealing with a 0 vector. So that's exactly what that is. So I will go to N2. N2, you talk about k norm of x. K norm of x. I show that is equal to modulus of k norm of x. Okay, so we'll be dealing with N2. N2 now. N2 you'll be talking of k norm of x LP, which is equal to summation I counting from 1 to infinity of absolute value of k here, k xi to power p, everything to power 1 over p. Okay? Of course, this k is to power p. Everything inside here is to power p. So I can bring it out, meaning that this is equal to summation I counting from 1 to infinity of of uh, of um, of k to power p xi to power p, okay, everything here including this one to power 1 over p. So this dissenting as this k is a constant because it's not affected by it, so I can bring it out, but I won't forget to power 1 over p. So if I do so, I will have k to power p to power 1 over p. And then summation I running from 1 to infinity of xi to power p to power 1 over p. Okay? Of course, p to power 1 over p will only make this one positive. So which will be modulus of k. Okay, summation I running from 1 to infinity of modulus of xi to power p to power 1 over p. What is this? This is equal to modulus of k. Modulus of k. Modulus of k norm of LP. So you see that k norm of x LP is equal to norm of modulus of k norm of x LP. This is exactly what N2 is saying, verifying N2. Okay, so modulus of norm of k x is equal to modulus of k norm of x. Okay, so that's for L norm of LP. Now we proceed to show triangle inequality. But to do that, you will encounter an object that you just have to use Holder's inequality. I will only start and then I will give you the hints. So you conclude the assignment and you can submit with it. Okay, so look at this. For N3, I have norm of x plus y, norm of LP, of course. Okay. Now you want to show that this is less than or equal to norm of x LP plus norm of y LP. That's exactly what you want to show. That's what you want to show. You want to show that this is less than, that's triangle inequality. Okay. But then if you begin to show this, you are going to encounter you're going to encounter, just like we did encounter the Cauchy-Schwarz inequality, you're going to encounter something like summation of xi, yi, okay? And of course, you talk of 1 to infinity. This by Cauchy-Schwarz inequality, you just have to resolve it using Cauchy-Schwarz inequality. And what does it say? I say Cauchy-Schwarz inequality, Holder's inequality. Holder's inequality states the following, that if you have A and B are sequences, AI, okay, I counting from 1 to infinity, and you have another sequence, BI, I counting from 1 to infinity. If they are sequences, okay, and they are in LP, of course, Holder's inequality holds in LP. You have the following, you have that summation, I counting from 1 to infinity of absolute value of X of AI. We are picking up sequences AI. So of AI plus AI, not plus, but BI, AI times BI is less than or equal to summation I counting from 1 to infinity of AI to power P, AI to power P, everything here to power 1 over P, and then summation I counting from 1 to infinity of BI to power P, everything to 1 over P. So you will this BI to power P, I'm sure you know that, to power P, everything to 1 over P. So you are going to resolve this, you substitute it just like we did for the Holder's Cauchy-Schwarz inequality. So in trying to verify this, you will encounter this, just make this substitution and the job is done. So that's exactly what you are going to do, and the job will be done. Okay, so that's for LP. I define a norm on LP. Let's also do the same for L infinity. I'm sure you recall L infinity has to do with the space of all bounded sequences. We've been able to define a norm on LP. So let's also see the norm on L infinity. These norms are fundamental. They are popular, and most of the times they occur in problems, and you must be conversant with them. So let's define the norm on L infinity. Okay. Look at the norm on L infinity. If I call it as a proposition, look at the function, define the function. Of course, you know the norm is a function. So, okay, the norm L infinity is a function with a domain. The domain itself is the vector space L infinity, and the range is the 0, infinity. Okay, you define that norm as follows. Defined that norm as follows. Norm of x, the vector x bar, L infinity is always the sup norm, equal to the supremum. Of course, your I varies from 1 to infinity, I greater than or equal to 1 of the modulus of all the xi's. Okay? Of course, this will happen for arbitrarily vectors x bar in L infinity. Of course, you know x bar, arbitrary vectors are infinite dimensional. You never can finish it infinite dimensional. They belong to L infinity, obviously. So you want to show that, claim that norm L infinity is a norm. Is a norm. Okay, so L infinity, this norm is a norm. So to show that, you have to show that L1, N1, N2, N3, all those axioms are all satisfied. Okay? Okay, let me start with some of them, and then you can round up the remaining. Okay, so I proceed as follows. To show that N1 is satisfied, you have that N1, you have to show that norm of X bar L infinity is equal to 0 if and only if you are dealing with a zero vector. Okay, that's exactly what N1 is all about. But then uh, uh, L infinity norm, how is it defined? Is defined as the supremum as I varies between 1 and infinity of the modulus of all your xi. If this is equal to 0, what's the meaning? Supremum of this is equal to 0. That will happen if and only if and only if,
xi 0.
yeah, if and only if xi, x1, if you like, break it up, equal to x2, equal to x3, equal to so many other things, right? All of them will be 0. Is it not true? Is it not true? For the supremum of any set to be 0, of course, all of them, because modulus of all of this is 0, right? So that is because supremum is the what? Is the least upper bound, right? So all of them will be 0. So what's the meaning of that? If all of them will be 0, what's the meaning? This will happen if and only if you are dealing with a 0 vector. Okay? Satisfying axiom N1. Okay? So that's for N1. For N2, I have the following. For N2, you have that norm X bar L infinity, which is defined as the supremum I the greater than or equal to 1 of the modulus of xi. Okay, so usually we do k dot, right? K dot, k dot, kxi, kx bar. This is equal to, because you are taking supremum over all the i's, and k is not affected by I. K is only affected by the absolute value. So I can bring out that absolute value K supremum I greater than or equal to 1 modulus of xi. What is this candidate? This is K norm of x bar L infinity. Okay, exactly. If you have kx bar and then norm of that, you can bring out the k like we've done here is equal to modulus of k norm of x bar L infinity. That's exactly what axiom L2 says. Satisfying axiom N2. Right? Axiom N3 is the famous triangle inequality. Axiom N3 is the famous triangle inequality. Let's also show that axiom N3. For axiom N3, I have the following norm of x bar plus y bar L infinity. What's that? This simply equal to supremum over all the i's greater than or equal to absolute value of xi modulus plus absolute value of yi also modulus. Okay? I'm sure that's so clear to you. Absolute value of xi plus absolute value of yi modulus. Okay? So you remember one of the properties of this. This is less than or equal to supremum I greater than or equal to 1, okay, of what? Of xi modulus plus supremum I greater than or equal to 1 absolute value of y I modulus. Which is this? What is this one? This is simply norm x bar L infinity plus, what is this one? This is simply norm y bar L infinity. So what have you done? You have just shown that this norm is less than or equal to norm of x bar L infinity plus norm of y bar L infinity. That's a triangle inequality now. Is it not? Is it not? Satisfying
Bro,
entry. Yes,
hello, I have a question. So
you can go
the
ahead.
norm of x bar plus norm of y bar L infinity is the same as the supremum of absolute value of xi plus yi naught.
Are you talking of this?
The first line, the first line.
The first line, norm of x
Yeah,
bar plus y bar is, of course, by definition, I'm sure you recall how the supremum norm is defined. This will be the supremum of x. This one is modulus of xi plus this one will be modulus of yi.
yes.
Okay,
Okay.
anyway, it's because I broke it up. Let me not break, let me share a new slide. I understand your worry. I jumped one line. I thought you will
Yeah.
follow. That's why I jumped it. But let me not jump. Let me share another slide and put it together the way it should be. You know, when I thought you are learning faster, so I decided to exclude about 2 lines. So what I'm saying is that norm of x bar plus y bar L infinity is simply supremum I greater than or equal to 1, okay, of what? Of xi plus yi. At least you understand this one now,
Yeah.
right? Aha.
Right.
This, look at the line that I jumped, the one I jumped. This is equal to supremum I greater than or equal to 1 into xi. This is triangle inequality is obeyed, so plus yi. Is it
Yeah.
not?
This is what I'm.
And
Yeah.
this is less than or equal to supremum I greater than or equal to 1. For this one, you have xi plus, for the other one, you also have supremum I greater than or equal to 1 yi,
Yeah,
right?
prof.
What is
I
this candidate?
understand.
What
Yeah.
is this candidate? Okay, yeah. This is
My
norm
co-
x
my
bar
question
L
is
infinity. Yeah. Okay.
my question is I
Yes.
want to make sure that the first and the second line is fine because supremum is out now. So since our supremum
Yeah.
is out, so this one is fine. Just we can proceed from the first one to the second one.
Exactly.
Okay, that's what I want to
Uh,
know.
It's okay. But you get it now, right?
Yeah, yeah, I understand.
It's okay. Okay. So I think we impose one more example and then we can close from there. Let me give one more example. This one has to do with function spaces. The function spaces, once again, function spaces, the space of all functions. Okay. Let x, that's yet another example. Example, let x be CAB. Okay. This denotes the set of real valued functions on an independent variable, t and also continuous. C means that it is continuous and continuous. You already know what we mean by that. So if that is the case, it means that elements of this space are functions. So if they are functions, you can pick up elements like F, G, they belong to this space C, A, B. Okay, if they are function, I can define vector addition. So the elements are vectors here are functions. So you can talk about addition of functions F plus G, for instance. F plus G, of course, the independent variable T will simply be F of T plus G of T. Okay, and then you can also talk of vector multiplication, which is lambda. You can pick up lambda F of T is equal to lambda F of T. So with this, you can show that this space is a linear space. Okay, with this addition and vector multiplication, scalar multiplication, vector addition and scalar multiplication, you can show that it's a linear space. And if it's a linear space, then we can impose norm. I'm going to give you the norms, about 3 of them, popular ones. So I can give you about 3 norms defined on this space. So you can now go home as an assignment to show that those norms are norm. Okay, let me just give you about 3 norms. Of course, you can see for yourself that CAB is a vector space with respect to those vector addition and scalar multiplication of functions. Okay, look at these 3 norms. The first norm, I call that norm F because the elements are norm. Let me call it the infinity norm. Let's use the infinity norm, which is the supremum norm. Of course, you take supremum as t varies from A, B close bounded, the modulus of F of t. You can show that this is a norm. The second norm, let me call it norm 1, which is equal to the integral A to B of F of t dt. You can also show that it's a norm. I have another one, this norm 2, integral A to B, okay, of the modulus of F of t, okay, with respect to t to power half. Okay, so show that norm infinity, norm 1, norm 2 are norms on CAB. Okay, that's your assignment. So you show that there are norms on CAB. Okay, so that's our lecture for our class for today.